Okay, and let's come back and continue on our detection theory. This is let's see, this is page 60 for your reference. If you are reading this along with your textbook, I think that would be easier. That would be easier, and you can take notes. You can take notes. Okay, so now we go to chapter 3. We go into statistical decision theory. So in this chapter, we are going to lay the basic statistical groundwork for the design of detectors of signals in noise. Let me just zoom in a little bit. Okay. So we are going to talk about design of detectors in noise. Then an important concept is the hypothesis testing. As you can recall from previous classes, I talk a lot about statistics. And in fact, you can see this as a more rigorous version of statistics because a lot of things are related to hypothesis testing. So for that's why I always talk about uh, H1 and H0, right? Recall that? In the first class, I talked about H1 and H0. That's a standard notation for hypothesis test. And also in chapter 2, we talk a lot about the distribution. Why? Why do we need to do that? Because as a preparation, we need to prepare for hypothesis testing. When we do hypothesis testing, it relates to statistics, and the distribution of the signal and noise. All those things would require the basic knowledge of distributions. That's why we talk a lot about distributions in chapter 2. And as I remind you, uh, in fact, there are a lot of different distributions. Uh, the Rayleigh, the Rayleigh, the chi-square, the F distribution, those are just some common ones. When you do your research and you encounter different different kind of distributions, I would suggest you to search search. There are a lot of documents talking about different distributions in the internet. Nowadays, the internet has more information than ironically, the library. Usually 20 something years ago, people would say if you have a unknown distribution, you like to know its property, you go to a library and you check out a book with hundreds variety of distributions. You check that book out from the library. But nowadays, it seems like we have more information on the internet, and people have been putting those things on the internet. So let's say you like to know a certain distribution, you just check it, and then they would give you the distribution, the the mean of the distribution, the variance of the distribution. Some of them even include moments of the distribution, the second moment, the third moment, the fourth moment, and things like that. Right. So to understand hypothesis testing, the fundamental thing is you get a solid knowledge on the distributions. Okay. All right. So um, we will address the simple hypothesis test problem, in which the PDF for each hypothesis is known. right? Because generally speaking, there are a lot of different types of disease detection problems. Some with known probability density function, some with unknown, and some with known distribution without knowing the parameters. And, there are a variety of those things. So there are different combinations. But we will start out easy. We'll start out easy, which is to say that we are going to start from the most simple examples. Okay. You see, a much more complicated problem will arises when the PDF has unknown parameters. We defer that later, okay? So the primary approach to simple hypothesis tests is the classical approach based on the Neyman-Pearson. You got to remember the name of the theory, Neyman-Pearson. I'm saying this because this is very fundamental. Trust me, this is very fundamental. Uh, Along the way of your career, if you are continuing in the area of communications or signal processing, communication systems, and things like that, uh, from time to time you see this theorem very often, and there are another name. In fact, they are different. We should not confuse. Neyman-Pearson is one approach. Bayesian is another, and they have different philosophy. So the Bayesian approach based on minimization of the base risk. In many ways, these approaches are analogous to the classical Bayesian methods of statistical estimation theory. We'll talk about that later, because estimation is about continuous parameter, as I mentioned in the first class. Okay, so we'll do that later. And the particular method depends on our willingness to incorporate prior knowledge about probability. Notice that there is a terminology, prior knowledge. Conceptually, I like to explain this first. Prior knowledge means something that you know a priori. Something you know a priori. I think it's interesting. A priori is a Greek, or it's like a Greek word or something. You may not know that well. To put it in plain English, is something you know in advance, meaning that you know that before you do observations, before you do estimations, detections, before everything that you do, the information is available to you. Those information are called prior knowledge. Okay, so prior knowledge about the probabilities of occurrence of various hypotheses. Okay, so the choice of appropriate approach is therefore detected by problem at hand. Uh, different applications has different philosophy. So some use Neyman-Pearson and some like to use Bayes approach. And here's a summary. It goes like which chapter says what, but it doesn't matter. We will go by our own pace. We'll go by our own pace, and some of them will be skipped. So yeah, we'll just go move on our own. All right, now here we come to page 61. The first thing is we talk about Neyman Pearson. Neyman-Pearson. Neyman-Pearson uh, is we can just use a simple example of hypothesis testing to illustrate the Neyman-Pearson approach. Okay, assume that we observe a realization of a random variable whose PDF is either 0 and 1 or 1, 1. Uh, this is somewhat, it looks somewhat strange at the beginning, but in fact it's not. Recall in chapter 1, we mentioned about something like 0 plus noise and 1 plus noise. You recall that example? That is actually corresponding to this distribution. If you have 0 plus W, remember that the name that we use is W. 0 plus W, then that would be distributed with 0 and 1. Given that W has variance 1, and 1 plus W has variance 1, and mean equal to 1. Okay, so I'm just talking about the problem. I mean the model of the problem. The notation denotes a Gaussian distribution with mean mu and variance sigma squared, that's which is standard, and we are not worrying about that. And we must therefore determine if mu is equal to 0 or equal to 1. Notice that this 1 and 1 is identical, so the 1 is not an issue. It's a variance, but it's not an issue because there is no difference between this and this in terms of variance, but there is a difference between this and this in terms of the mean. So we are concerned about the mean. Okay, so we must therefore determine if mu equal to 0 or mu equal to 1 based on a single observation x0. Then each possible value of u can be thought of as a hypothesis, so that our problem is to choose among two competing hypotheses. They are summarized as follows. Okay, so that hypothesis testing problem is summarized this way. If it's given h0, mu will be equal to 0. If its hypothesis 1, mu is equal to 1. And then we can start to write down its distribution. The distribution of x, we have a problem here because we have not defined what x is, right? But as I mentioned, x is in fact distributed this way or distributed this way. Let's just say that way. Okay, let's just keep this for now. So if p of x given as h0, then it's what? It's distributed this way, this. So when it's distributed this way, then it will be 0 and 1. So you see things like this, It has 0 mean and variance. Variance is like the width of this distribution. And then if mu is equal to 1, then that mean has equal to 1, like this. And then variance 1, so the variance is 1. So you see the distribution like this, and then you see another distribution like this, and you see, if we just not look at this for now, let's not look at 1/2 for now. You see two different distributions, and then the problem is, how do you set up a threshold to decide which which hypothesis it is for a given observation? So previously we would just say 1/2. Then I make an example about if a person comes up and say 1/3, and the other person like to set a threshold differently, then what are we going to do with that? So this chapter is going to give you a detailed analysis. Then you get a sense of what happens when you set different thresholds. So H0 is referred to as the null hypothesis. That is actually the what? It's just a name. It's a name. Okay. In fact, it's okay. Let's just read it and then I'll explain. Then H1 is an alternative hypothesis. So the thing is, if we are doing, for example, binary problem BPSK, it doesn't matter which one is null hypothesis, which one is alternative hypothesis, right? One could be 0, the other could be 1. Alternatively, if you like to put this as 0 and this as 1, it doesn't matter. So in digital communications, those names are not that important. The importance is you make a correct decision. That's more important than the names here. But statistically, there are some historical reasons, so people use the names null hypothesis and alternative hypothesis. So this is a binary hypothesis test. Since we have to choose between two hypotheses. Okay. So the PDF under each hypothesis are shown in figure 3.1 with the difference in means causing the PDF under H1 to be shifted to the right. This is shifted to the right. On the basis of a single sample, it's difficult to determine which PDF generated. Okay, so let's go to the next page. Page 62. Page 62. A reasonable. Let's not look at this first. Let's read it and then I'll explain what happens here. A reasonable approach is to decide x0 larger than 1/2, then you decide h1. This is because if x larger than 1/2, the observed sample is more likely, right? Here we are going to step by step building up the concept. Before we go into the complicated mathematics, we like to build up the concept step by step. So to make it easier to understand. So the observed sample is more likely if H1 is true. Right? If you look at this 1/2 here, at the right hand side, H1 is more likely because its probability density is higher than H0 here. Right? So if X To put it another way, if x0 is larger than 1/2, we have from figure 3.1 that p x conditional h1 larger than p x conditional h0. So if it's larger, then we'll see this larger than that. It's more likely, or mathematically, the probability is higher. Okay, so our detector then will compare the observed datum value with 1/2. So this is called a threshold. I mentioned multiple times, but here we have a formal definition for the terminology threshold. Okay, and notice that with this scheme we can make two types of errors. If we decide h1 but h0 is true, we make type 1 error. Okay, let's take a look. If a sample comes up here, and then we will say it's from h1. But unfortunately, the truth is it may come from h0. Then we are making a mistake. And that type of mistake, we will say type 1 error. Which means that we decide h1, then well, in fact, the h0 is the correct ground truth. Well, the other way around, if we decide h0 by h1 is true, we make a type 2 error. We see it here, type 2 error. You condition on h1, and then you make a decision on h0, meaning that you are making mistakes in this area. Okay, so there are two types of error, type 1 error, type 2 error. But again, in digital communications, it's not important. The name itself is not important. The error is important, but the name is not that important. The issue is that we want to make mistakes as less as possible. As less as possible. Okay, so so for example, P of this, how does this happen? It happens when you condition on h0 and then the decision is h1. You make a mistakes of this error and probability of this larger than that condition on h0, right? So that's when x0 larger than 1/2 condition on h0. I suggest you to think carefully on this because this is very fundamental and very important, yet it's a little bit abstract. When the x is larger than 1/2, we are making decisions of h1. Think about it, right? We are making a decision of h1, but in fact, it's h0. So the probability of h0, conditional h0, we get a sample larger than that. That is when we make mistakes. So that's this area, this dark area, this area, right? This area. That's when we make mistakes of type 1 error. The other way around, if the sample is smaller than 1/2, then we have a mistake of another type because condition on h1, you are making decision on h0. That is the probability density function. No, that's the probability in this area. Okay, so that is called type 1 error probability. Then The other one is the type 2 error probability. It is not possible to reduce both error probabilities simultaneously. Let's think about it. If you shift the threshold, you are reducing one type of probability while you increase other type of error probabilities, right? You set a threshold here and try to draw the figure one more time, and then you put it here. You put it at different locations and then see what's going on, and you will find that it's not it's not likely to reduce the two error probability simultaneously. If you reduce one error probability, you are going to increase the second type of error probability. Okay, so here comes the signal model. If we view the problem as an attempt to distinguish between the hypotheses, this hypothesis has only the noise H0, X0 equal to W. H1 equal to signal plus W. And then if we set S0 equal to 1, then the W will be distributed by this normal distribution. Then we have the signal detection problem, right? As I said, this has what? This has distribution. It has only W, so it has distribution, this one. The next one, oh, we have here. W0 is distributed here, right? If you put a 1 here, you get a distribution with mean equal to 1. That is identical to the distribution we talk about here. Right. So I think that'll be consistent, and it explains what happens in the beginning of the chapter. That this is a signal model, right? And then as a result, this is referred to as the probability of false alarm. Usually, this is null. This is alternative. If nothing has happened, which is H0, and then you decide your decision is that H1 has happened, then that's a false alarm. 中文叫做误警报，误警报 P probability of false alarm 误警报，就是没有事情，然后侦测的结果说有事情，这个是一个误警报这样子。false alarm. Then we denote it by PFA. Okay, and usually we like to set a small value of this one, but of course it depends on applications. This is not like absolute standard for this. No, it would be highly dependent on applications. To design the optimal detector, we then seek to minimize the other error or equivalently maximize this. So we are talking about this probability of false alarm, and then we will set up a desired value for PFA, which is what? Which is something we like to constrain. We constrain PFA below a certain level, and then we seek to minimize the other error P, H0, H1, or equivalently to maximize 1 minus P. This thing and this thing are mathematically equivalent. Okay. So, but again, this is so-called Neyman-Pearson criteria. Neyman-Pearson. Okay, Neyman-Pearson philosophy is to say that let's set a threshold. Let's set a threshold on PFA and then minimize the other type of error. So let's take a look. And then H1 is something good because it is a detection. It is a detection. Something has happened, you detect something has happened. That's a correct detection. That's a good thing to do. So that would be detection denoted by PD. Okay, so that is called Neyman-Pearson approach to like hypothesis testing or to signal detection. So in summary, we wish to maximize PD equal to H1 subject to the constraint PFA equal to alpha. In other words, PD is something we like to have as much as possible. Good thing to have. We like it. The constraint PFA is something we don't like, so we try to avoid it. We try to set a threshold on it, which is the PFA equal to alpha. Then we maximize PD with the constraint PFA equal to alpha. Okay, then now we can return to the previous example. We constrain PFA by choosing the threshold gamma things. PFA is the probability of H1. Let me clarify the notation a little bit. When we put something in front of the semicolon, meaning that we decide our decision is H1. Our decision is H1. So we decide on H1, condition on H0 as a ground truth. This is what? This is the first false alarm. The false alarm. So if we set a threshold gamma, for example, we set a threshold gamma here. Conditional H0. Conditional H0 its distribution is actually like this. Right? Like this. Then we set a threshold. Then it's the px0 larger than gamma. That is what? That is the probability of this area. This small like triangle. In fact, it's not a triangle, but it's like a small probability here. So you have PR of this larger than gamma conditional H0. And of course, then you know this is a Gaussian distribution, right? It's a Gaussian distribution. You like to do integration from here up to infinity. So you do from gamma to infinity. And this is the Gaussian distribution of x. Then at the end, you obtain the Q of gamma. Recall what we did in chapter 1 and chapter 2. We have a defined Q function as the integration of Gaussian distribution from gamma to infinity. Right? That has been defined. So as an example, if PFA equal to 10 to the minus 3, we have gamma equal to 3. We therefore will decide H1 if x larger than 3. So previously, when we talk about 1/2, now we have a better understanding of it because we know the threshold sets a value of probability of detection and sets a probability of false alarm, right? All those things, they are related. So now it's not arbitrary anymore. Now anyone comes up and say he would like to set a threshold somewhere, Now you have a mathematical foundation to discuss with him, and you know what effects he's going to have for that threshold. So for this case, 10 to the minus 3 and gamma equal to 3, we therefore decide this for that. And how do you know 10 to the minus 3 corresponds to gamma equal to 3? That is the question, right? That is the question. I would say that would be solved numerically. That needs to be solved numerically. Because PFA, if we set it to 10 to the minus 3, it becomes Q gamma equal to 10 to the minus 3. Then you have to find a gamma value that corresponds to 10 to the minus 3, which is not trivial. It cannot be done by hand. It has to be done numerically because Q function has no closed form. Okay, and then furthermore, for this choice, we are going to have PB equal to PH1 condition on H1. Condition on H1, x larger than gamma, is the same thing here, except it's condition on H1. Then your distribution is distributed at the mean of H1, which is 1 here. We have a lot of ones, right? So this is the Gaussian distribution with mean equal to 1. Then it will be Q equal to gamma minus 1, which is equal to Q of 2. And then Q of 2 is 0.2023. Of course, then you can try to solve it numerically, right? Numerically, or if there is a lookup table, you look the table up, and then you know Q of 2 is something like this. Again, this is numerical. This is not analytical. Okay, so we have a layer foundation for mathematical rules for you to understand the threshold. Very important thing, the threshold, and the threshold is going to cost you probability of false alarm, probability of detection, and things like that. So it's not arbitrary anymore. Now you have a mathematical foundation for that discussion. So now we are at page 63, and I think that will be the end of this session and also the end of this class. And uh, again, we are not going to have a physical meeting in the classroom. Please do not come to the classroom. Okay, and that's the end of this class. And thank you for listening. We'll continue on next week. Thank you.